on condensed matter and statistical physics, A1, organized by the Department of Physics, Presidency University, Kolkata. And just a note to all the participants to please turn off your camera just to save some bandwidth and keep yourselves muted. If you have any questions, you can write in the chat box as well. So, as our speaker, Professor Ricardo Dias, is here, so without much delay, I would like to hand over the mic to our departmental head, Professor Urunobu Chakraborty.
I try to generalize this concept of square root topology to high root topology. And I'm going to do that introducing first a particular set of one-dimensional models, which we call n-time squareable sine-cosine chains. And then I'll present a general method for construction of high root topological insulators. And then I'll summarize, okay? Okay, so if you want to look up some more details about what I'm going to show you, you can look up these references over here, okay? The ones from last years are the most important. Of singular behavior starts at the monopole and extends to infinity. And whatever you choose, you will always have this Dirac string. We call this line of singularities a Dirac string, okay? So let's now jump to two-level system. The most general Hamiltonian for a two-level system, excluding global shifts of energy, is this one that you see here, where the cursor is, okay? And if you look at this matrix, you will conclude that it's a linear combination of Pauli matrices, okay? And the components of this linear combination define a 3D vector that here we call D, okay? D, it's this vector over here. D. Sorry, okay. And if you find the eigenvalues of this matrix, you get plus and minus the magnitude of D. And if you find the eigenbases, these eigenbases can be written using the spherical angles of this vector D. So theta and phi are the spherical angles defined by the vector D. And it means that the two levels are degenerate. So when I have a degeneracy, it creates flux, this very flux, okay? So how is this relevant to topological insulators? Well, let's consider the most simple example of a topological insulator. The most simple example of a topological insulator is the SSH ring, okay? Or the SSH chain, if you want. The SSH chain is a 1D system with alternating hopping terms, or alternating hopping constants. T1, T2, T1, T2, T1, T2, and so on. So it has a unit cell with two sides, okay? Let's assume periodic boundary conditions. So we have a ring, and let's find the eigenstates bottom bed. That's what we saw just a while ago in the SSH model. For T1 equal to T2, they would touch, okay? So let's go back to the 1D system. I have this bulk Hamiltonian for the SSH model. I'm going to call this off-diagonal matrix element, I'm going to call it rho. Rho, it's a between cells, unit cells, and the other calculated within the unit cell. This one is a very recent one where you project the Zach space into a particular sublattice. And this one was also very interesting, where you have an artificial dimension. And then instead of calculating Zach space, you calculate the Shen number, for instance. But the one that we want to explain today, it's this one. We square the Hamiltonian. Okay, we square the Hamiltonian. So let me show you what this means. And I'm running a little bit behind. So yes, I'm running a little bit behind. Okay, let's assume a uniform chain. So a uniform chain, and I'm going to assume also it's a ring. So its tight binding model, it has this matrix representation you see here. It has nearest neighbor hopping equal to T1 and on-site energies equal to epsilon 0, okay? It's this model that you see here, but now I'm going to set epsilon 0 equal to 0. The reason is the following. Models or tight binding models where we only have finite matrix elements in the Hamiltonian between sites in different sublattices, and here I'm just considering two sublattices, they are called bipartite, okay? So for instance, here, this model is bipartite because I only have finite matrix elements of the Hamiltonian between sites blue to red and red to blue, never blue to blue, okay? And when I have that kind of Hamiltonian, I have chiral symmetry. In fact, chiral symmetry, the chiral operator is just the projection in one sublattice minus the projection in another sublattice. But that's too much detail. Okay, it's models that are bipartite. I can define two sublattices and only have hopping terms between these two sublattices. They have chiral symmetry. Let's square this Hamiltonian. If I square this matrix over here without the epsilon zero, I get a block diagonal matrix. And you may not believe it, but it's there. It's there, and one of the blocks corresponds to the odd sublattice, odd side sublattice, and the other one corresponds to sublattice. Okay, the red and blue. And one of these blocks, the block for the blue, corresponds to a tight binding Hamiltonian with a hopping term T1 squared and local energies, local on-site energies equal to 2T1 squared. Okay, every site has this energy. And the other one, the other block, is exactly the same. In fact, these two chains, these two smaller rings, have exactly the same spectrum. Okay, and the eigenstates of the original ring can be written as the linear combination of the eigenstate for the blue sublattice plus the eigenstate for the red sublattice, but these two eigenstates must have the same energy, okay? The red sublattice and the blue sublattice. And in fact, it's easy to show that why the spectrum is chiral. It's chiral because if we multiply the amplitudes in one of the sublattices by -1, we still get an eigenstate, but with symmetric energy. Okay. So what are we doing here? What we are doing is basically taking a chiral spectrum. This is the spectrum of this ring over here, okay? We take this chiral spectrum and, we square it. And by squaring, we fold the negative part onto the positive part, okay? So we would have all the levels on the positive part. But if we remove, notice now the following. If we remove this 2T1 squared, this blue ring becomes bipartite again. So again, if I remove these uniform local potentials, this ring becomes bipartite. So it will have again a chiral spectrum. So that's what we are saying here. We take a chiral spectrum, we square it, we remove some energy, and it becomes chiral again. And then I can do the following. Can do again the same. Square it, shift energy, obtain a chiral spectrum. For the uniform chain, I can do this until I reach two sites, for instance. And notice that I have here levels with different colors, and these correspond to the chiral level. And when I mean the chiral level is this central level here, okay, the zero energy level. So the different colors on the top, here on the top, correspond to the different chiral levels that are appearing. Notice also that it's a different chiral symmetry every time, okay? So I have initial chiral symmetry of the initial ring, I squared, I get this ring, I remove the uniform chain, uniform local potentials, I get a new chiral symmetry. These are different. So this can be generalized for any bipartite, whoops. Sorry, someone is presented.
I think somebody is presenting.
No, stop that.
Preeti Mishra, can you please stop yours? Okay, now it's fine.
Oh, okay, I'll need to
Sorry,
present
sorry for
again.
that, Ricardo. Yeah. Just speak on
sorry,
that.
Professor Dias, you can continue.
You want me to? Do I need to stop presenting then?
No.
No, it is fine.
It's fine.
It's fine. Oh, it's fine.
Someone by mistakes just
Okay.
on that person, yeah.
Let me. Okay. I hope that you're seeing. Let me just put this larger because I don't know why, but it became very small here in my screen. Well, I know why. But I'll continue. It's not very fun. So I was just saying that we can do this for any bipartite model. Okay, any Hamiltonian that has this structure that you see here, okay, only off diagonal block, it only has one off diagonal block, so we can basically define a sublattice, and I only have hoppings between one sublattice to the other sublattice. This one, when squared, they generate this block diagonal matrix. Now, it's not mandatory that these two blocks have the same dimension. Okay, in the case of the uniform chain, they did, but maybe they don't have it. And if that happens, what the spectrum of two blocks is still the same, except that one of the blocks has extra zero energy states. Okay, extra zero energy states. So, and in fact, these zero energy states only have finite, only have support in one of the sublattices. Has this been applied to the topological insulators? Yes, it has. For instance, in this paper that you see here, people address the diamond chain with a pi flux. Okay, so when you have a diamond chain with a pi flux, all the bands in the band structure of the diamond chain become flat. You get a flat band with energy 2t, sorry, a flat band with zero energy, and another flat band with minus 2t. And if the diamond chain has open boundaries, it's not a ring, then you get also edge states. And these edge states have finite energy, as in the case I mentioned just a while ago. And they have their energy is square root of t and minus square root of t. The Sachs phase of these free bands is not quantized, except the central band. Okay, but if you square this diamond chain, you get this spectrum over here. And now the bands that you have, they have quantized Sachs phase. Okay, they have quantized X phase. And notice that this blue band over here, it has two bands. It's genetic. The two bands are the two bands. It's basically these two blue bands here, and only one red here. And one of these two blue ones is the chiral partner of the red one. Okay, it's the chiral partner of the red one. And in fact, we can remove again this 2t square energy, and we can say there is a chiral symmetry for these two, for this pair of two bands. And these edge states, in fact, are protected by this chiral symmetry. But okay, in the paper you can look some of these details. There have been quite a few already experimental realization of these square root topological insulators. Okay, and this is the same paper that I've shown you before in a photonic lattice. And but there are other realizations in acoustic lattice, topological lattice, even some mechanical with springs and masses, and they have done this, in fact. So acoustic lattices are interesting. It's basically a sequence of cavities connected by small channels where you create sound. It's basically that. And topoelectrical circuits are basically, it's electric circuits with capacitors and inductors and all of that. And you can simulate topological insulators and square root topological insulators on that. And here you have an example which is called the breathing Kagome. The breathing Kagome, it's a weak topological insulator and also a higher order topological insulator, but that's not something I want to discuss here. But anyway, you can see the edge states are here in blue and here in blue. So you see that they get finite energy edge states, okay? And these red ones are what we call corner states, but well, let's keep that. Okay, so I want to generalize this. I want to generalize this to high root topological insulators. How I'm going to do it? I'm going to introduce these sine cosine models. How long do I have? How much time do I have still?
Yeah, you have time. You have time. You have time at least 15, 20 minutes.
Oh, okay, that's good. That's good.
Ricardo, will it be possible to make it bigger? You are having difficulty in that because
this one.
Yeah. Actually, we are all seeing a small patch of your presentation.
Okay. Let me share it again.
Because of that glitch, I think something went wrong.
Oh, okay. Resume presenting.
Yeah. I think it's becoming. Yes. Yeah, I'm seeing it. It's becoming nice.
Screen, it was
yes.
large. It was large,
yeah. It's fine. It is
That's
fine. Yeah.
Oh, okay. Okay.
Yeah.
So I was saying I want to generalize these two high root topological insulators. How am I going to do this? I'm going to introduce a new type of 1D systems that I'm going to call sine cosine models, or called sine cosine chains. The second simplest sine cosine chain is the SSH chain. The simplest one is the uniform chain. But let's consider the sine cosine chain. So the sine cosine chain, as I told you before, it has a unit cell with two sides, and the hopping terms are T1, T2, T1, T2, and so on. If we divide these hopping terms by this square root, okay, by the square root of t1 squared plus t2 squared. Then t1 over the square root becomes a sine. T2 over the square root becomes a cosine. So we get this chain over here. Sine, cosine, sine, cosine, sine, cosine, and so on. If we square this, it's fairly easy to understand what appears here. Okay, let me explain just once. For instance, let's take a particle here in this pink side, okay? I'm considering the Hamiltonian squared. So the Hamiltonian does not generate just one hopping. Squared, it generates two. So a particle hops once, hops twice. Okay, that's what happens. So assume that we start at this pink side over here. It hops to the right with a hopping term cosine, and then hops again to the right with a hopping term sine. So the effective hopping term between this pink side and that pink side there, it's going to be cosine sine. And but we have other possibilities. We have this, for instance, the particle is here. It hops to the right with hopping term cosine and hops back to the initial side. That generates a cosine square. But we also have the possibility that this particle over here jumps to the left and jumps back. And that leads to a sine square. So we get cosine squared to come back plus sine squared to come back. And that gives 1. Okay? So that's why squaring this chain over here, you get this chain over here. Okay? Fairly easy. Okay? Now let's introduce a more complicated example where the unit cell now it's larger. Okay? Can we do this? Look, it's a bipartite model. We can always square and get a block diagonal. But what I want, it's not to do this once. I want to do this several times. And that's what I'm going to call my generalization of the square root topology. Because square root topology, I could only do it once. But now I'm going to do it twice, 3 times, whatever. Okay? So I define here a sine cosine model with a unit cell that has 2 times n sides. And that means that we have n different angles theta. So I have sine of theta 1, cosine of theta 1, sine of theta 2, cosine of theta 2, until I reach sine of theta n, cosine of theta n, and then it repeats. Okay? So 2n sides in the unit cell, n angles. And if I square this, it's the same reasoning as before. So I get 1 everywhere. Why do I get 1 everywhere? In the pink sublattice. Because this pink sublattice is surrounded by sine of theta 1 and cosine of theta 1. So going right and back, going left and back keeps sine squared plus cosine squared of the same angle. But now the sublattice, the blue sublattice, it's not going to be the same as the pink sublattice, the Hamiltonian for it. Okay? Okay, that's important. In fact, the block corresponding to the blue sublattice is no longer bipartite. Only one of the blocks is bipartite, which is this pink sublattice after I remove this uniform chain, okay? Uniform local potentials. So I got this. And now what I pretend, what I want, what I want is to remove this energy and still get a sine cosine model, okay? Now it's not. You look here and apparently it's not. It's not a sine and here a cosine. It's something more complicated. But I'm going to select a particular set of angles that when squaring, I get again a sine cosine model. What I have here is exactly the same model as on the top, but just the bulk Hamiltonian. When I have, I'm going to say this very quickly. So when I have a one-dimensional system with a unit cell of a certain size, the bulk Hamiltonian is just the Hamiltonian for the unit cell, and then I close the unit cell on itself, and I put a flux, which is the momentum. That's the bulk Hamiltonian for 1D systems. And that's what you see here. So it's the same Hamiltonian for the unit cell, and then I close the unit cell on itself with a phase, which is basically the momentum. Okay, so I'm going to consider a particular set of angles, and then I'll say how we define these angles. I consider a particular set of angles, and for this particular set of angles, I get this band structure that you see here. So this has 8 sides in the unit cell, so I get eight bands. And now I'm going to square it. Just the bulk Hamiltonian, because this is enough to give me the band structure as I square it. Remember that the bulk Hamiltonian is still bipartite, only has hoppings between pink and blue sublattice. Okay, so it has chiral symmetry, and that's what I get. So I square it once, I will get a chain that's still bipartite, still has the sine cosine form, but has uniform local potentials equal to 1. I remove this. Okay, I'll remove this 1. And in fact, it's not exactly of the sine cosine form, because it's multiplied by this global hopping. Okay, this global hopping. Do you remember that in the SSH model, I had to divide T1, T2 over the square, divided by the square root of T1 squared plus T2 squared in order to get it in sine cosine form? It's the same. So when I square this model, I get this model over here with uniform local potentials equal to 1 that I remove. And this model is a sine cosine model times a global hopping factor, something that I multiply everywhere. Okay? Now I take this one over here, I square it again, and this is only for one sublattice, as I mentioned before. Okay? For instance, here I only pick the pink sublattice, but here I choose the blue sublattice. It can be whatever we want. And again, I get a model that has uniform local potentials equal to 1 that I remove. And again, it's of the form sine cosine if I divide this by some global factor. And in fact, this one is already the SSH model. Okay, this one that you see here is the SSH model. And I can do this until I reach a unit cell that only has one side. It's the uniform chain. Okay, so I start with this band structure. I multiply it, shift it, divide by some constant, I get this one. I square it, I get this one. Square it again, I get this one. And all of these have a new chiral symmetry. Okay, all of these. Can we do the opposite? Because, okay, we started with the result, to be honest. Can we do the opposite? Can we start with the uniform chain and build this chain? And build this chain with the gaps that we want and the bandwidths that we want. Yes, we can. Okay. In fact, the parameters that define the bandwidths and the band gaps are these global factors. These T0, T1, T2. If I know this, I know the initial band structure. Okay. It's quite funny. I start with a uniform chain with only one band. I define these global hopping factors. And now I can do this step backwards. I can do it backwards because I have these expressions. These are the expressions that are going to define the angles of the top models. Okay, so I use these expressions, and these expressions almost uniquely define the angles. There is a small degree of freedom, but it's discrete, sometimes two solutions. Okay, so that's fine. Squaring, because as we said before, squaring selects a sublattice.
Yeah.
Okay, but this, in this case, it didn't need to square it, but it's always there. Okay, it's always there. In the same way that here, when we define this chiral symmetry here, this is the chiral symmetry of the squared model. This one over here. So it's, in fact, all of them have connection. The only one that does not have connection, I would say, it's this one over here, where they have the extra connection.
Right. Okay, I can just read out only one more question because we have a few more, but I will request the persons asking the questions to mail Professor Diaz because we have other talks now. And the last question I would pick up from this is from Moitra Kundu. Can you shed some light on how the 2 to the n root these may be experimentally realized? Can you really experimentally realize this?
Okay, I can. For instance, the first realization that we hope to do, we are working into frameworks, basically. We have one here, we are trying to do the acoustic lattices here in my department, but we are collaborating with people in Barcelona on photonic systems. And the sine cosine chains are very easy because we only need different hopping terms. And these hopping terms, so a photonic lattice is basically a silica crystal, and you carve waveguides with a laser. Okay, you can carve the waveguides with a laser. And the distance between waveguides defines the hopping terms. So the sine cosine chain is very easy to do. You just have to define these waveguides with particular distances. Okay, so that's easy to do. Also easy to do is topoelectrical circuits. Topoelectrical circuits now are very fashionable because you can do everything. You can do Hermitian models, non-Hermitian models. You can do great things with it. It's not very expensive, and we tried. To be honest, we applied to a project with people from Lisbon to do that, but the project was not so successful. So that one is not going forward with real systems. Take a graphene sheet, okay, a graphene plane, and you start carving it, making holes. That's one way of doing it. You can change it in such a way that you get this high root topological oscillators, in fact, a high root version of graphene. That's another way to do it. But that's experimentally a little bit more difficult. But that's another way.
Okay. I still see questions floating up, but I think we should, for the time being, stop here. And we must thank Professor Ricardo G for a wonderful exposure to the topological issues of systems using very beautiful models, which one can definitely work out by hand and can look into many more possibilities. Ricardo, thank you very much.
Thank you, Arnav. It was
like
a pleasure.
To have you with
Great
us
to see you again.
Yeah. It was a real pleasure for me, and maybe I will be talking to you later about some queries of my own. But for the time being, I am handing over this session back to the coordinator with a big thanks to Professor Ricardo G again for an excellent
Thank you
talk.
very much.
Thanks, Ricardo.
Bye-bye.
Yeah.
Bye-bye. I'm stopping the share.
Yeah.
Thank you, Professor Dias, for this excellent talk. Also, I would like to thank AC sir for chairing the session. And here we are at the beginning of our oral presentation session at this afternoon part of the conference. And I would like to hand over the mic to Poulomi to take charge of this session. So, Poulomi, please.
Thank you, Shobhit. Good afternoon, everyone. Now we are in our second session of oral presentation. Here we have two talks, and the rules remains the same for the speakers. You have 15 minutes for your presentation, and the next 5 minutes for our question answer session. I would like to request all of the participants to please turn off your camera, and also please keep yourself muted. You can write your questions in the chat box that will be addressed to the speaker at the end of the presentation. Now, I would like to welcome our first speaker, Dr. Narasimharao V. Avvaru from Rajiv Gandhi University of Knowledge Technologies, Ongole. Are you there? Dr. Avvaru, are you there? I can see him in the participant list. I guess
he's yet to log in.
He is still in the meeting. He is in the meeting. He needs to unmute.
Maybe he is gone
It's a
somewhere
network
for
issue.
network issue. Maybe he has just taken a couple of minutes off due to some reason. So
Yeah, he has got.
it's actually
Dr. Avvaru, you can unmute yourself.
Yeah, he writes yes, ma'am.
Dr. Avvaru, you can unmute yourself and start your presentation. Can you hear us? Dr. Avvaru, I guess he responded also in the chat box. Now it's over to you, Dr. Avvaru. You can start your presentation.
Hear what is happening. Just let me check.
He's writing his microphone is not on. Something.
Oh, he's writing something in chat box.
Yeah, in microphone or not. You can.
Oh,
There is a
my.
microphone button. You can just click on that.
Avvaru,
That
you
will.
can please try to turn on your microphone because your
You
presentation
can
is
turn on your
scheduled
microphone and
3:45.
Yes, please click on the symbol of your microphone. That is the first step. I think he's rejoining. He's trying to rejoin. There must be some
yeah,
network
Okay,
issue here.
I think we can skip to the next presentation and just shuffle it back. Right, we have
yeah,
two
we
talks.
can do that.
Just let us wait for 1 minute, Paulomi.
Yes, yes.
In case he rejoins,
Okay, sir.
so
Okay,
let
let
us.
us wait till 3:45.
Otherwise, we can ask the next speaker to start presenting. And just in that case, please write a message to Avvaru that we are placing him next.
Okay.
Start your presentation now.
My
Yes,
PPT.
please. Your screen is visible.
Good
Yes,
afternoon, all of you. I am A.V. Narasimharao. My presentation is micro machining characteristics of silicon in NH2H added KOH solution. The main mode of this study is improving the etching characteristics of silicon for MEMS applications, for industrial fabrication of MEMS structures by increasing the etch rate of silicon. Microelectromechanical system. Microelectromechanical system is the integration of mechanical elements, sensors, actuators, and electronics on common silicon substrate throughout microfabrication technology. MEMS have two components, electrical components and micro components, mechanical components. MEMS-based devices can range in size from few micrometer to millimeter, have ability to sense actuate on micro scale. Why MEMS?
Going to talk about effects of magnetic anisotropy on reversal of magnetization in Bloom-Keppel ferromagnet. So first of all, let me mention the plan of my talk. First, I will briefly discuss the metastable state in a magnetic system, its lifetime, associated classical nucleation theory, which explains such dynamical problems nicely. Then I will describe the model and simulation technique. And after that, I will share some various observations regarding reversal or metastable lifetime under the influence of magnetic anisotropy. Then there will be conclusion along with some future scopes, followed by some useful references. So first, how does a metastable state appear in a magnetic system? So that question can be addressed very simply in the light of free energy versus order parameter picture, where this free energy is the Landau free energy. And this is a very well-known picture of free energy versus order parameter for the Ising system, where below critical temperature, the system has two stable states. Now, and this is in absence of any external field. Now, if we apply some external field to that system and below critical temperature, then we found that immediately this symmetry breaks and local minima appears here along with the presence of a global minima. And this local minima actually indicates here the appearance of the metastable state. Now, if this applied field is sufficient to overcome this energy barrier between this local minima and this global minima, then only this metastable state can decay to this stable state. Am I audible? Hello?
Yes. You are
Okay,
perfectly
yeah, fine. Okay, so now let's say how we have defined the metastable lifetime or reversal time of magnetization. So first notice this plot, magnetization versus time. where initially we have considered a perfectly ordered state. That means almost all the spins are +1. So magnetization is 1 here. Now, as we apply some negative field to that system, then it is generally observed that the system first enters into a metastable state, and after a long time, it suddenly decays to this stable state. That means here now the spins try to align along the direction of the applied field. And here, quantitatively, we have defined the metastable lifetime or the reversal time of magnetization as the time at which this magnetization just becomes starts becoming negative. And we have used this definition of lifetime or the reversal time throughout our work. Okay, so now how does this metastable state decay to the stable state? And that is nicely explained by the classical nucleation theory, which assumes that the free energy for the formation of droplets of down spins into the sea of up spins is actually formed of two terms. This is the bulk energy term, and the second one is the surface energy term. And due to the competitive nature of these two terms, there must be a presence of critical size of the droplet such that the droplets, only the droplets with size greater than LC are energetically favored to grow continuously, and only they can take part in the reversal. So the main point is here that the metastable state decays to the stable state through this nucleation process. And later, in 1935, Baker and Doring predicted by some analytical calculations that the rate of such nucleation process is strongly dependent on this energy barrier or this critical energy corresponding to this critical size of the droplet. And so definitely the metastable lifetime also depends on this critical energy. So this is a very brief theoretical background of metastability. But in this work, actually, we have done simulational studies. And am I audible?
Yes.
Hello? Okay. Yeah. Fine. Okay. So people started such computer simulational studies a long time back, which is around 1970. And there are many important papers on metastability, metastable states, metastable lifetime, etc. And here I am mentioning only 3 of them, and this is one of such important papers. And here authors studied the metastable states and nucleation in kinetic Ising model. Also, there are some other 2 papers. In that paper, authors studied the dependence of metastable lifetimes on field, system size, etc. in kinetic Ising model. Here also is Shomadip.
It will be better if you can ask directly.
Yeah. Decay of metastable state to the stable state. Yeah. Hello?
Yes, just carry on.
Not symmetric or hello?
Yes, you can speak out. Everybody is listening. We can hear it.
Shomadip?
Shomodip, are you listening? Or you have an issue with
Shomodip?
Yes, Shomadip is there, I think. Shomadip is there. I think he's facing some network issue.
maybe, but I think he can hear actually.
He can hear us. Oh, he's saying that I am writing. He's saying that he's writing.
Okay, fine.
Okay.